Thank you for the invitation. I just want to present maybe better to say an overview on what I mean with the word reconstructing curves. But I want to start with the general form because something very little, but something can be said in general. So, and hopefully can be said more general later. Okay, it's not working. Okay, it's working. It is a joint work, it's part of a joint work. The results are a joint work with Gian Pietro Pirola and Enrico Schlesinger. Okay. So the general setting is this one I want to set down. So we take x in P2n plus 1 as smooth hypersurface. I will work over C. Smooth hypersurface. I set to n plus 1 just because then I need the numbers to be good, but it's really not necessary that the dimension x is odd. It's just easier to write down. And I fix d to be the degree of x. And a famous theorem of Griffiths, I do not want to enter in special descriptions, but I just want to say that a famous theorem of Griffiths tells you that there is an isomorphism between primitive cohomology classes, Hodge classes, cohomology classes, like H, P, Q of X prime, to a certain degree. I want to write down in general the degree, but a certain degree of the Jacobian ideal Rx. So where Rx is the Jacobian, the Jacobian ring, nor the Jacobian ideal. This is the sum of H0 O P to n plus 1 of, if we say n of n, mowed out by the Jacobian ideal in degree by degree. Those are graded rings, so degree by degree by the degree of polynomials. So it is the Jacobian ideal. This is clearly the ideal generated by partial derivatives. Of f, where x is defined by f equal to 0. So what's the point? So the smoothness here of the hypersurface is crucial because if x is smooth, the partial derivatives of f doesn't have common zeros, so it is an Artinian-Gorenstein ring. And what's the point for us? The point is that whenever we take a class, we can attach to a class polynomials, and hopefully those polynomials that are easier to study polynomials can give us back informations on the class. So this is what I mean with, I will explain better what I mean with the reconstruction. I just write down that the case we will use. So where P is equal Q is equal to N, and I don't want to deal with the Hodge conjecture. I start with something that is algebraic because not all the classes are, as far as we know, algebraic in general. For course, it's always true. Algebraic means that it comes from a real subvariety, algebraic subvariety of x. So y, I start with y in x smooth. I put parentheses because for course we can drop these hypotheses. In general, we cannot because it's harder to deal with higher dimensional varieties. So we still take the smoothness, but it's not, should hopefully not necessary. Smooth subvariety, algebraic subvariety of dimension n. So it's like I put the 2n here to have just the n feather. So we start with y. To y we can associate a class inside Hn of x. And the primitive part of this Hn, the Griffiths theorem tells you that is isomorphic to the degree m plus 1 d minus 2n minus 2. So there is a formula involving p and q, d and n in general, but I will just use this. The degree is not important. What's important is that starting from a class, we can associate in a standard way polynomials, and we try to understand better those polynomials to get back and to reconstruct the curve. There are many results in reconstruction that's classical in this sense, like Torelli theorem that tells you that a curve can be reconstructed by its Jacobian, and also many important results of Griffiths and Harris. For instance, Griffiths and Harris for curves proves that if you have a fundamental class with the same numerical numbers properties of the class of a line, it is actually the class of a line in your surface. So there are many reconstruction results really deep. What I mean with reconstruction is what I try to say really roughly here. So we start with y in x, we associate to y its class, and to the class of y there is a standard way to associate an ideal. I will call it E alpha y later, inside the R of x, so it's an ideal of polynomials. Actually, I will try to sketch the construction of this ideal in the case of curves. We actually define the ideal inside the H0 of O of n, and this ideal contains the Jacobian, so we can mod out and recover this. So it's not really important. Sometimes I will confuse, let's say, the ideal in the space of H0 of On and in the Jacobian ideal, so modded out by the Jacobian ring and modded out by the Jacobian ideal, but really that doesn't matter so much. So we can find an ideal that has been defined in many ways already by, I probably forgot someone, many people, surely by Voisin and others. We will follow a more constructive and useful way to define this ideal. It's a more algebraic version, because all these things can be, I won't present a more, let's say, more algebraic version of this, but it can be done at Griffiths and Harris done with periods and some more like this, more algebraic version following Ellis, Grund, and Peskin. So there's a way to attach to it a polynomial, and the properties of this polynomial is obviously what we hope to expect is that clearly the Jacobian ideal, if we do not define it in the ring but in the general, more general ring, not in the Jacobian already, but the homogeneous ideal of y. So the ideal of the equations, the defining equations of y as a variety of x is contained in this ideal alpha y. So inside these polynomials, there are also the polynomials defining y as a variety. So it is exactly what we expect for what I will call, no, maybe it's too long, for reconstruction. So for me, reconstruction here really means under which conditions we have equality here. So the homogeneous polynomials is exactly our ideal. Our polynomials are exactly the polynomials defining y as a variety. And this should be true. It's known again from Griffiths, Harris, and so on. This should be true for D sufficient. D is always, I recall here, is always the degree of the hypersurface is bigger than the degree of the subvariety. Okay, for D sufficiently large, it should be true. In the work, if I have time, I just put, but it's not that important, the bound in the work with the Pietro, Pirola, and Enrico Schlensiger. In the case of curves, we give explicit bounds for this thing. But for this sufficiently large, it should be true that we exactly reconstruct the curve algebraically from these equations. But one can also observe that the class here, there could be there could be other subvarieties. There could be another subvarieties, let's say y1 inside of x. Again, subvariety of dimension smooth, always as before, of dimension n as y, with this defining the same class or the same ideal. So for sure, as we said before, also the defining equation of y1 are contained in E alpha y. So hopefully, because this could not hold for the lower degree of the hypersurface, hopefully we can make a more generalized, I don't know, it could be generalization of reconstruction. This is what Movasati and Sertöz in a work in, I think, 19 or 2020, called perfection. So what we can hope for lower degrees, we can hope that they define a class, let's say a class of y is perfect. Those are always those are always graded ideals, so degree by degree. So we fix a degree is perfect if there exists other subvarieties y1, yk. I just put in x as before, subvarieties, smooth subvarieties of dimension n, with defining all the same ideal for every I. And here we do not have that the only polynomials in our E alpha y are the polynomials defining y, but the polynomials defining y plus the polynomials defining the other subvarieties related to y's. So the sum degree by degree, sorry. So degree by degree, the sum of E, y, a degree m, y from 1 to k. So hopefully the best what we can do with this polynomials is to reconstruct not just the curve, but all the curve, sorry, the subvarieties, so it will become a curve in a minute, the subvarieties and the other subvarieties related in this way to y, defining the same class. So the question that Movasati and Sertöz pose in their paper is that are all the so I got lost.
Yeah, you got stuck a second.
Okay.
I stayed.
Oh,
The last thing I understood
okay.
was when you said, "Oh, the question of Movasati and Sertöz is," and then.
No, okay. Big question if are all the classes perfect? So the best we can do. So the general reconstructibility, but it's my definition is not we always use the word perfect. So this is what we can hope for the best. There are examples they knew because it's new before just for I think Griffith error, so maybe Alice Grunde-Peskin for sure they knew, Movasati, Dan, other knew that if Y is a complete intersection in intersections of variety inside X, then it is perfect. So there are examples of always for every degree here of the polynomials, but also for every degree of the subvariety, they're always perfect. But unfortunately, it is not true, and we have counterexamples. But we have also counterexamples. I just say it, but we can go back later because now I want to start with speaking about defining this ideal, speaking about curves. There are counterexamples and curves. It is what we found with Pietro and Enrico. So C is a quartic rational curve inside S that is smooth again, always quartic surface in P3. And here, the quartic here, the homogeneous ideal is generated by cubics. So if you look of cubics defining this ideal, at level 3 it is not perfect. So I just stress here, and then I will say more on this. E alpha C degree. So if we look for cubics in our ideal, we will for sure find the cubics defining the curve, and we working on it find the cubics defining another curve related to C in this way. This is still a quartic rational curve. We find the cubics of the Jacobian, but we find more, and this more is no way to find another curve related to C, and those cubics are the cubics defining the other curve. There are no more curves except for C and D in the class, so we do not have any other version of this, but here we find extra polynomials. So the way is that we try to understand how to find those polynomials here, and we try to find if there are extra polynomials, meaning no of this type, no one of this type. So there are, it's not true there are the classes perfect, but we don't know we do not have a condition for perfectness. We know something that is perfect, we know something that is not, but we do not still have condition also for the easiest case of curves. But we have also in higher dimension here, n is always the dimension of the subvarieties, so double to have the dimension of the hypersurface. Where do we equal? We have Franco and Villa from Loyola, I think is the way I have to pronounce it. They found counterexamples they found counterexamples not studying exactly this problem, but they call it fake linear cycle because they relate it to another problem. But they found counterexamples for Y containing X of degree it's the degree of X 3 or 6. There exist counterexamples. always, infinitely many families of counterexamples. But it's not a classification. They found out that those subvarieties, those cycles, those classes, because they are looking for another problem. So they end out on these classes, and they found that those classes also are non-perfect classes, but it's not a classification. There could be more also for other degrees. But there are counterexamples. Still, we do not have any condition on this. The easiest case where we can understand what's going on is the case of curves. If you do not hate me, I will change my notation. So I will call what was before y c, because this is a curve and as a surface in P3. This could be easier. Okay. As I said before, we follow what Alice Group and Peskin did. They did it studying the Noether-Lefschetz locus. Noether-Lefschetz theorem tells you that for D is always the degree of S, sorry. D greater or equal than 4, the general surface has Picard rank 1. So the Noether-Lefschetz locus of degree D are a surface of degree D with Picard rank greater or equal than 2. And surfaces we are interested in are exactly surfaces in the Noether-Lefschetz locus, because if we consider our general surface, all the classes of the curves are complete intersectional multiples of the hyperplane classes. So we have no more geometry to study. We are no interesting to know. So what we will define actually is non-trivial when we deal with a surface in the Noether-Lefschetz locus. So they define those algebraic version to study this loci here. So the problems are really related also to all the classical literature on the Noether-Lefschetz loci. Okay, I don't want to enter in many computation. I just say what we need. So we start with an easy exact sequence for our situation. So of S of minus d, that is the degree of S, goes to omega 1 of P3 restricted to S to omega 1 of S and 0. So it's an exact sequence. Okay, taking cohomology. Taking cohomology, I just write down what we need. We have that H1 of omega 1 of P3 restricted to S, that is generated by the class of a hyperplane, goes to H1 omega 1 of S, that is our H11 of X. So the thing that we want to study. And here I just write down what I said before. H11 of X primitive is isomorphic. This degree fits to our 2D minus 4. In this case is 2D minus 4. It is really H11 of X. So H11 is H1 omega 1 of X of S. So here we can consider the hyperplane class here goes to the hyperplane restricted to S. So we can mode out here by the class of the image of the hyperplane. And these are exactly the primitive classes. Sorry, X is an S. the primitive classes. So there are the classes that are not complete intersection multiples of the hyperplane class. So here, okay, this is non-trivial when we are in another Lefschetz loci. So we just consider non-general surfaces, and then here just we have non-trivial classes. So we go to H2 of OS minus D, that is third dual to H0 OS for D, 2D minus 4, and this 2D minus 4 is exactly this 2D minus 4. And here we can consider a class, or here if you want, already in the quotient, we consider a class that is a class of curves that are algebraic, and we associate to it an alpha C in the dual. The dual means that it is a linear form from H0 of OS to D minus 4 to C, because it's in the dual is a linear form. So we define our E alpha C exactly as the annihilator of alpha C. The annihilator means exactly degree by degree. Degree M are the polynomials in H0S. So degree M such that alpha C of F, they are in the kernel of alpha C. Clearly, we start from OS in degree M, so G should be in the dual with respect to D minus 4. So OS 2D minus 4 minus M. Okay, this is exactly the kernel, let's say the annihilator, the linear form. So we can define E alpha C as the annihilator of this linear form, and this alpha C we will see is exactly the ideal inside as we define inside H0 degree by degree of OS, containing, and we will see that it contains the Jacobian, so it's exactly, if we mod out the same ideal as before, and it's exactly the ideal we're looking for to attach to our C, to our class. Okay, and we see also that alpha C is 0, so the ideal is all the space. If we are in the C is linearly equivalent to a multiple of the hyperplane class if it's complete intersection. So again, if we want something that is non-trivial, we have to work with another Lefschetz loci. What I have to say more? Okay. This is not, unfortunately, this is not constructive, but we have, up to now, we see that clearly if S is general, we do not have C giving us an annihilator that gives us something non-trivial, but it really belongs to S, this annihilator, and if we go further using deeply C, we can define another element easier to understand related to this alpha C, and this element, it will be another annihilator, is the thing that will really help us to find explicit condition to work with, to find examples or counterexamples. So constructive method. Start with C and with another, again, exact sequence, the normal bundle exact sequence. So the normal of C and S, that is omega S degree 4 minus D. It goes the normal of C in P3, that goes to the normal of S restricted to C, that is O, C, D. Yeah. So again, we twist by minus D and take homology. And we get that we start here. H0 of NC minus D goes to H0 OC. That goes to H1 omega. Sorry, S is the C. Or degree 4 minus D, that is third dual to H0 of OC in degree 2D minus 4. Again, 2D minus 4, the same as before. It's not a case. Okay, here we can do this idea. We take the one here and we go to the image of one is a linear form in the dual. Again, is linear form, so again, something like this, and we can take the, again, the annihilator of beta C. Okay, that could be seen more or less with caution as the kernel of this map here. And we see that the kernel of this map here, for the exactness, is again exact sequence, is the image. Maybe I can put names. Is the image of this P here. So those are exactly the properties that the main properties that we know that the annihilator of this beta C is really related to the image of B. Maybe degree by degree, because degree by degree we have here we can twist by a degree, and we have exactly degree by degree. Those are graded. Graded, the image of B is not graded, but graded mean here we put an M here and here, and we have PM if you want. Okay, and also we have that the main things that our alpha before is the pullback by a pi of this beta, whose pi. Here we have H0 of OS, let's say degree by degree. Here we have M, here we have pi, the restriction to OC. Here we have H0 of the normal bundle of degree N minus D, and this is B. And here it is not important, but we have delta, and we have H1 omega C for minus D minus N. Okay. So pi is this map, is the restriction map from H0 of S to H0 of omega C. So the annihilator is again, as before, the annihilator of alpha C is in H0 of S, the annihilator of beta is in H0 of C. And we have this, oh, sorry. This property. And we have also the other property that's pi minus 1 of the annihilator of beta, that we will confuse degree by degree with the image P, is contained in what we called E alpha Y, the annihilator of alpha. And the equality, if and only if pi is surjective. Again, pi, I just recall what we will be interesting for us. Which color? Pi is surjective for every M, if and only if, like a definition. C is an arithmetically Cohen-Macaulay curve. So being that one of the definitions that we can use H1 of the ideal of C on degree N is 0 for every N is one of the definitions. So it's surjective because the kernel of this is the H0 of the idea. So being an arithmetically curves means that pi is always surjective. So here we have just that annihilator of C is exactly pi minus 1 of the annihilator of beta, so we can study the annihilator of beta and have all the information of this more involved and more hard to study ideal. In general, so not all the curves, for instance, if C is a complete intersection, then C is an ACN curve, and C twisted cubic is an ACN curve. Those are the most known examples, but just to understand what I mean. Sorry, I got an okay. So this is true. Pi could be surjective for some m. So again, the equality here is the something that we can study degree by degree. Okay. So I rewrite here what I said. Pi minus 1 of the annihilator of beta is contained in E alpha y. And also that stupid remark that the kernel of pi, so pi minus 1 of 0, is the the homogeneous here, the homogeneous idea. Sorry, why? I still write why my this is C. Is the homogeneous ideal. So the homogeneous ideal of so the H0 of the is the homogeneous ideal is clearly the kernel degree by degree still here we are graded. Okay, it's the kernel of pi. So we see that pi minus 1 here, so this tells stupidly that this is contained inside the alpha C because the pi minus 1 of 0 is contained here because here can be seen degree by degree, but the image of beta because of the exactness of this sequence. So the curve here is the image here. So pi minus 1 of 0 is containing here. So it's containing here. So we're dealing with something that we're interested in. And I don't want to stress this thing, but here we can consider the H0 of the tangent bundle and that have a map here and a map here, and the image of the H0 of the tangent bundle is the Jacobian ideal. So again, the Jacobian ideal in this diagram is contained in pi minus 1 of the image of beta. So again, in E alpha C. So when we have equality, I don't want to now consider the Jacobian ideal because we can think of mode out by the Jacobian ideal. How we have equality? We have to be equality here. So the kernel is contained in pi minus 1 of the image of beta, but the image of beta should be 0. So to have the equality, so we have that H0 of the normal bundle in degree m minus d should be 0. And then we have to be equality here. So the equality here means that degree by degree, pi surjective, and pi surjective means that the dual is injective. So we can consider this condition. H1 of the ideal in the dual 2d minus 4 minus m is equal to 0. That means that the dual is injective, so the pi at the level m is surjective. Those two things are the things that we have to have that at degree m, our ideal is exactly the ideal we found out and we defined before. So they are explicit, and if we found out a way to give explicit bounds that clearly depends on m. we came out with general bounds with no dependence of M because we set that M is the minimum, clearly, degree in which EC is generated. For instance, in the example before of the C quartic, quartic M is 3 because 3 cubics generated the quartic. So we just fix M to be the degree in which they are generated, the ideal is generated, and we drop out the dependence of M. Otherwise, those vanishing condition depends also on M. Okay. So we can have bounds. Maybe I don't want to stress those things because they are numbers. And the condition is this one. And we can find more thanks to Ellis-Grunner-Peskin. We can find that if C, we know that C, we know in general, but in particular, in particular for I don't know where I was writing. Okay, in particular for complete intersection in general, so in particular also for curves, we know that complete intersection are perfect classes, and we know that complete intersection are examples of ACM curves, and we're happy that we can generalize these things thanks to Alem, Ellis-Grunner-Peskin, that if C is an ACM curve, then it's perfect. This is what we did with Pietro and Enrico. This is due to a lemma that gives us a surjection. We have something. Okay, no, I don't want to write, but there is they prove a lemma in which they found that a certain sum of cohomology groups surjects over E alpha C, degree by degree. And working on these cohomology groups, we found out that these cohomology groups gives us just things as the ideal of a curve we started with and the ideal of curves related to in the way I explained it before. So these cohomology groups gives us just ideal of curves related to C. So it's perfect. Unfortunately, it's really deal with the property of being a curve. ACM for sure, because it really needs the resolution of the ideal property of the ACM curves. But for curves, maybe it could be extended to codimension to ACM subvarieties, but I'm not sure. But codimension to subvarieties in our problem means that we can deal with surfaces in dimension 4 hypersurfaces and no more, because we have codimensional is always n for every n. So unfortunately, we don't think that in this way, in the way it's proved for curves, can be generalized for every ACM. So it still open the question if, let's say, for every n, ACM subvarieties are perfect. And we don't know the answer, because unfortunately we cannot use this again. And we found, as I said before, counterexamples. Just explicit in explicit examples. What we did for the counterexample is just starting with C, so we know what is the ideal of C. Let's say we fix 2 cubics because cubics generates the ideal. We know this ideal, and we study the condition. We study the condition E alpha C equal to E alpha D, and that exists as TMP in status, maybe. Giving not relatively prime and non-zero for sure, such that as the H plus T C plus P T is linearly equivalent to 0. So we study this condition of defining the same ideal, the same class, and we find just only one other curve, D. This is again a smooth quartic, curve. That is an intersection, again, I said that S is a quartic surface. And there is only one quadric containing the curve C. And this D is exactly the residual intersection between the quadric and S. Because one intersection in the quadric and S is C, and the other curve is D. And this is the only one satisfying this condition. So again, we consider the Jacobian in degree 3 because clearly it's a quartic, so there are 4 partial derivatives for cubics. And then we consider the cubic here, we consider the cubic here, we consider also the intersection, so what we already counted. And still we have no more things because we have no more curves. We already counted this, we already counted all the things that we have to count, but still this is not enough because we know exactly that the dimension, the number of the dimension of this is bigger. We can compute it. It's bigger than the sum of these things. So we found an example in this way. And as I said before, just to say what we know in the bigger dimension. In bigger dimension, we have many problems, but one of the problem is that we don't know in general the Hodge conjecture, so we start with something that is algebraic, but this is a relative problem because we just consider something that we know already that it's algebraic, so why should the class of Y should be algebraic? Oh, sorry. And we can define again E alpha Y and the annihilator of beta Y as before. Roughly speaking, we take the wedge n of all the previous excess sequence and we get mostly the same. What's more difficult? Then we get longer excess sequences, so we get more vanishing conditions. As before, because before we had something like H0 of S degree by degree, H0 of OC, if we can now say X and Y if you want, OX, OY, and here we have something to H0 of OY in the degree, the one of the Griffiths, so n+1 times d minus and so on. And here we have the H0 and the normal and blah, blah, blah. This is as before, but this map here is a composition of maps because it's longer. So here we have to deal with vanishings and we have to be careful of speaking of what we have here. So we have more vanishing condition that gives examples more difficult to find. So we have an algebraic description of we already have a description of the ideal, the alpha y. What worth it of this description is that using this constructive method, we can exactly make computations and examples better than before, if we can define these two things, but these still already difficult to deal with. They are not that usable, but there is a way to define algebraically those as before the things, but it's quite more difficult. We're trying to find examples. Still, we do not know nothing for ACM subvarieties. We do not know if they still extend, as I said before, complete intersection. Yes, they are perfect. And we still, also for n equal to 1, we do not have a condition for let's say, general reconstruction. Condition for reconstruction, as I said before, we have it, the two vanishings, or here are the more vanishings. But for general reconstruction, so if we can have, also for curves, we don't know if ACM is the biggest class of curves that can be reconstructed in the general meaning, the perfection meaning. If we do not have condition, we just have examples and counterexamples. Counterexamples meaning that not all the class can be reconstructed. We have other, as I said before, founded by Franco and Villa for Loyola, examples in dimension of y greater than 1. Greater than 1. He found this example studying actually the generalization. As I said, surfaces, so hypersurfaces, if we use the general word, hypersurfaces and subvarieties that we are interested in lives in the Noether-Lefschetz locus. The generalization of the Noether-Lefschetz locus is what they call the Hodge locus. Maybe there is also an n here to remember the dimension, because for Noether-Lefschetz is always 2. So is the locus of hypersurfaces. So maybe I write it dimension to n, but just not to n degree d. So you want to study this Hodge locus, that's the generalization of the Noether-Lefschetz locus. So again, the ideals that we can define are non-trivial. Non-trivial means does not the quotient is non-trivial. Only if we deal with hypersurfaces in the Hodge locus. Okay, this is exactly the same. And a famous result of Green was tells you that if so for the Noether-Lefschetz locus, so surfaces, if d is greater than or equal than 5, then the locus has many components. The components of minimal codimension are the ones in which the surface is containing lines. So the aim of this work and other works is to extend this Green was on results to the Hodge locus. So is it true if the minimal codimension components are the ones containing linear subvarieties? In general, we don't know. We just know that what we know can prove that it's true for d greater or equal than n, that in our setting is 2n, so the dimension of x is true. And trying to find the counterexamples or examples of proving Green-Poisson results in the general case, Franco and Villafranca Loyola, I just say for special components, because I don't want to enter in the in this definition, but they cannot, they are not able to deal with all components, just because we really do not know. There are many problems in higher dimension. For instance, in general, we do not know also which is the minimum for the codimension of the. We do not know if which is the minimum, so it's really hard to find. So they restrict to subclasses of components in which we know which is the minimum and which we know more, and for these special components they found that the Green-Poisson is true, so clearly not lines but linear subvarieties of dimension n, except for d equal to 3, 4, and 6. And in these cases, they find what they called fake linear cycles, clearly fake linear cycles, because they are cycles contained in hypersurfaces in component of minimum codimension, but not containing subvarieties of linear subvarieties, but subvarieties that they call fake. Since those cycles are really explicit with equations, they can compute explicitly E alpha y, and they find that it's not perfect, it's not reconstructible. So studying another related problem, they find out that those are, for instance, are non-perfect, but still we do not, those are still examples. We do not have conditions or classifications or something like this to understand whether when we can have a general understanding, a complete reconstruction of our algebraic subvarieties from the Hodge classes or not. And maybe I stop here.